Namaskar, Adab, Sat Sri Akal. How are you, students? I hope that all of you are doing very good in your studies. So, if I am talking about our topic, ongoing topic, that is moving charges and its magnetic effects. Okay, my audio is very clear to all of you. I hope. Okay. So, if I am talking about that, we have seen about magnetic moment and these kind of things. We have seen about very important relation of angular momentum and magnetic moment. M by L is equal to Q is divided by 2M. In the last lecture, when we have seen these kind of things. Now we are in the final lecture of moving charges and its magnetic effect. Yes, we are in the final lecture. Finally, we will be completing this lecture. Okay, we have seen in complete depth. We have just gone for theory for board perspective majorly, and the competitive kind of variety of questions we have discussed, and we have gone in complete depth. Now we will be having our question series also, don't worry for that. As of now, just understand the concepts and now then come to the question series, then we'll be understanding all the questions also, how to apply these formulas. In which we are taking some basic questions also for your better understanding. Now in the last lecture, if I will tell you majorly, we are going to discuss about torque. Okay, how torque is applied. We are going to discuss about device that is moving coil galvanometer. Okay, these kind of things we are going to discuss. So let's begin without wasting any further time. Be ready with your pen and paper. Let's start. First thing is torque. Torque on a magnetic field. Where our pen is gone? Torque in a magnetic field. Okay. So if I will say that it is a uniform magnetic field that is applied here. If I will ask you, tell me what will be the net force. Firstly, let's calculate the net force, because you know from net force also we can say that, because what is the formula? R cross F. R cross F is the formula. So I can write from force what is our torque. See, firstly let's see for force. How I will tell you that how to find. This is the direction for current that is shown here. This is the direction for current. What is force on a current carrying wire? It is equals to BIL. Bill. You use this is the direct formula for force. And if I will be talking about the direction, how you find? I have told you anyways it is L cross B, but I have told you to do I cross B. I cross B. Correct? Do I cross B. I cross B. Here it is shown. Here it is the 2D diagram. Okay, here it is shown correctly. See, this is the current. Okay, this is the direction of magnetic field. Do I. Now I can have two options, either this way, either this way. Which way you will do? Magnetic field lines are coming outside the plane. That means you will do what? I cross B. That means which side you are having? This is the direction of force. Here what is the direction of force? I cross B. What is the direction of force? This one. Here if I will ask you, tell me what is the direction of force, I will say the direction of force will be this way. And here if I will ask you, tell me what is the direction of force, again this way. So can you say all these vectors, if magnetic field is uniform at every place, all these vectors are going to cancel out each other. If all these vectors are going to cancel out each other, what do you understand? That net force I can say is equals to, net force is equals to 0. Simply. Clear? And I will say if magnetic field is uniform and angles are here, you can say angle between B vector and M vector is equals to 0. You remember I have told you that there is a formula for torque also. Anyways, we will see further about torque. Firstly, let's understand how to derive the torque. I will tell you. I have not given you the formula, I hope. Now correct, I will tell you about the formula. See what you can do. There is a wire. Okay, there is a wire like this, and I want to calculate how much torque will be coming into it. How much torque will be coming into it. Firstly, I will check what is the direction of forces that I am having. What is the direction of forces that I am having? Okay. So, firstly, mention the direction of forces. Here it is already mentioned the direction of forces. This will be what? ILB, the force, the length of conductor, and here again it is ILB. And what is the length? Here it is taken as B. Now from the hinge point, if I am asking you, tell me what will be the net force, how you calculate? You always calculate the line of action of force, into the perpendicular distance. What is this perpendicular distance, students? This perpendicular distance is nothing but A by 2 sine of theta. Here if I will ask you, tell me what is the perpendicular distance, this is also A by 2 sine of theta. Correct? Both the perpendicular distance are A by 2 sine of theta. So how you write the line of action of force is this, and this is the perpendicular distance from this point. Correct? So if I will ask you how to write torque, torque is what? R into perpendicular distance. Firstly, you will be writing R. Net torque, if I have to write, this is the net torque. R, this is the net torque, torque. How will be writing? Force into perpendicular distance. Force I already mentioned, and into perpendicular distance. How will be writing? Force into what is the perpendicular distance? Here also a by 2 sin theta, and here it is what? Again a by 2 sin theta. So F into a by 2 sin theta, F into a by 2 sin theta. This a by 2 sin theta, a by 2 sin theta will get simply add up, and you will be writing force into a sin of theta. And what is force you have mentioned here, students? I into B into A, and there will be a theta also from this sin theta. So net I can say here you will be getting IAB sin of theta. Now what you can write for A into B? If you will remember from the last case, what is the length and what is the height that was given. If you will, I will be asking you, tell me what is A into B. A into B will be nothing but the area. So what you will be writing? I into A into B into sine of theta. Now tell me what is I into A? Current into area. Yesterday I told you what is magnetic moment? Current into area, correct. So I will be substituting at the place of I into A, that is equals to M, and then I will write B as it is and sin theta. That means this is the formula for torque. What is the formula for torque? M into B into sin of theta. So in other words, sin theta can also be written as M cross B. This is the formula for torque. M cross B is the formula for torque. Is it clear to you? Is it clear how you will be writing torque? Just check the angle between M and B and just do a cross product. I told you how to find the direction of M. Just curl your hand in the direction of current. It will always, the thumb will always give you the direction for M, magnetic moment. Clear? And if there will be n number of turns, then what you will be doing? If there is n number of turns, just multiply your result with n simply. That will be the answer. Correct? The receiver is not getting it. Correct. Now see, find the force on the wire AC. You have to tell me what will be the force that will be acting on this wire. This radius is R. What is the force on a current carrying wire? Current carrying wire between force point A and B. Force you will be writing. It is equals to I into effective length between A and C into B, that is already given. Just simply what you will be doing, calculate the effective length between A and B. I have told you to write effective length. If this distance is R, this is also, that means effective length is nothing but equals to 2R. That means it will be equals to 2R into B. That means finally what you can write as answer, which option is coming correct? 2 into IRB. According to me, option B will be simply correct. Simple. So basic application of formula. Correct. Option B is correct option. I have told you. Now when it will be maximum, when the torque will be maximum, when sin theta will be maximum, and at what value sin theta is maximum? Sin 90 is maximum. Sin theta maximum value is 1. So I will say magnitude wise it will be having its maximum at theta is equal to 90 degree. When it will be minimum, now don't get confused because magnitudes, what a negative sign just represent that it is not in the, if let's suppose it is applying some torque is applied in clockwise direction, negative means what? It is applying some torque in anti-clockwise direction. So again it is applying some force, but minimum will be what? When the effect will be least. I can say when torque is equal to 0. At what angle torque will be equal to 0? If theta is equals to 0. That means there is a angle between the magnetic moment and the magnetic field is equals to 0. Clear? So now let's discuss a little bit about non-uniform magnetic field. Till now we have discussed all the cases about uniform magnetic field. Now let's have a quick recap on how to solve the kind of problems of non-uniform magnetic field also. Very simple. I will tell you some steps. Just blindly follow those steps. Don't get deviated to other ways. Simply it is very simple. I will tell you how. Okay, let's start. Let's suppose here it is what given. There is an infinite wire. Force on a, and you want to calculate what will be the effect of this infinite wire, what will be the force that is felt by this second wire of length L that is given here. This is what you have to calculate because it will have some magnetic field. Okay, it will have some magnetic field, that means it will create some force also on this wire. So what is the force that is felt by this wire of length L? This is what you have to calculate. So what you will be doing, first step, always remember, go at a distance x and cut out an element. Go at a distance and cut out an element of thickness dx. And now forget about everything, just focus on this dx element and try to write about this dx element. What is the current flowing through this element? That is I2. And what is the current flowing through this infinite wire? That is I1. So let's write about this in further detail. And this point, mention all the, remember all the things. Here the distance is A and till the end the distance is L. So let's again read out this diagram from the scratch. I will tell you. This is one infinite wire that you are having, correct? And here it is the second wire of length L. This distance is given as A. This is already L. The current that is flowing here is I2 and the current that is flowing here is I1. Okay. Firstly tell me, you know what is the magnetic field due to this infinite long wire, correct? You know now how much mu naught I divided by 2 pi r. And in what will be the direction? I can say it creates a circular kind of thing, circular kind of magnetic field line. That means the direction of magnetic field intensity will be inside the plane, correct? Now let's see what I told you. First step, go at a distance x and cut out an element of thickness dx, and now forget about everything, just write about dx. How you will be writing? Now see, what is the force formula? Force on let's suppose this is wire 1, this is wire 2. I am writing force on wire 2. Okay. So what is the formula? B into I into L. If I will telling you in the I am not mention anything 1 2. I just tell you what is the basic formula, B into I into L. And now let's see that how you will be proceeding. Firstly, tell me what is the current that is flowing into this wire of ds thickness wire. Now forget about the complete wire. Just tell me about ds thickness. What is the current flowing? Can I say it is I2? Correct. Now tell me what is the magnetic field that is experienced by it. So what is the magnetic field experienced by this small thickness of element? Can you say this wire is creating that magnetic field, this infinite long wire? And what is the effect of this infinitely long wire for this small element? How will you be writing? What is the formula? You will be writing mu naught I1 divided by 2 pi x. 2 pi x. This is what the formula. Okay. Because the distance we have taken is x into what is the length? What is the length of this element? We have taken a length of dx. And what you will be doing, this is the small force that is experienced. Integration from 0 to f. Now tell what is from where to where you actually want to integrate this equation. I will say you want to integrate this complete. Can you say you want to integrate this complete wire? What you will be doing? Tell me what is the position of x here. What is the position of x here? Can you say x is equal to 0? Here what is the position? Here it is x is equal to a, and here what is the position? X is equal to a plus l. And you want the effect to be integrated from this point to this point. That means what is the from where to where you want to integrate? Actually you want to integrate from a till a plus l. That means from this point to this point you want to integrate the complete effect. Is it clear? Now tell me, force will be here. What will be the integration part? Rest of the things take common. Mu naught I1 I2 divided by 2 pi. Integration will be only for dx by x. Now tell me students, what is the integration of dx by x? Dx by x integration will be ln x. What is the limits? It is a plus b, and in denominator here it is a. Now put the limits. Here it will be what? It is a plus b divided by a. And here the constants will be written mu naught I1 I2 divided by 2 pi. This will be the force that is experienced. This is the force that is experienced. Is it clear? This will be the net force that is experienced by this wire, second wire F2. And if I will ask you what is the direction of this force that is experienced, how will we tell it? Let's suppose if this is the current, what will we be doing? I cross B. What is the direction that you are getting? This will be the direction for the force. Correct? Clear? Everything? Very good. Now after that, this is the complete integration that is shown here, and finally the result that you will be getting is mu naught I1 I2 divided by 2 pi ln a plus l divided by a. Now here the direction have been reversed. Reason is there because the direction that we have taken was going from A to B. That's why the force direction was coming upside. If you are taking the current direction from B to A, obviously the current force direction will be downward. That is not a big issue. Okay. Fine. Very good. So now if first was what the orientation was, firstly was this vertical plane and second wire was horizontal. What will be happening if I am taking this both as a vertical, what will be happening? So if the direction of current, always remember this, if direction of current for both the infinite wires is same, that means what kind of force you will be having? Attractive forces. If the direction of current will be opposite, for this one is going upside direction, this one is coming downward direction, then you will be having the forces in attract repulsive forces. Remember this thing. I will tell you why magnitude also, how the magnitudes will be coming. See, mostly in these kind of questions, they will be asking you force per unit length. They will not be asking you about the finite force. They will be asking you always force per unit length. So let's see how we will be coming to that. Let's suppose I want to write the effect of this wire 1 on the wire 2. That's why I have written force on wire 2 due to wire 1. How will be writing? Basic formula I into B into I into L. Tell me what is the current that is flowing in the wire 2. I am only focusing on wire 2. Tell me what is the current flowing through wire 2. That is I2. Correct? Clear? Now tell me what is the length. Length you are taking here. I have told you now, you are calculating for 4 per unit length. That's why I have taken the length as L. Now tell me what is the magnetic field experienced by this wire 2. From where this magnetic field will be coming? Tell me. From where it will be coming? From wire 1 it will be coming, and it will be in inside direction. And how much magnitude wise? It will be mu naught. What is the current in wire 1? Mu naught I1 divided by 2 pi. What is the distance given between them? That is D. That is equals to D. So simply I think that I got my result. This is 1. This is force on 2 due to 1. So what I force on 2 due to 1 divided by L is equal to mu naught I1 I2 divided by 2 pi D. This is the result that you will be getting. I have told you force per unit length will be mu naught I1 I2 divided by 2 pi D. Now they have written another one. No need to remember like that. If you have to put the values, what you will be doing? Why that is written, that I will tell you, because we know the direct result for mu naught by 4 pi. So sometimes you can do multiplied by 2 divided by 2. So that you can generate the condition for mu naught by 4 pi, and you know why I am telling you, because the value we already know, that is equals to 10 power minus of 7. That's why sometimes we take that value. Okay. Is it clear? Is it clear? Okay. Force per unit length. So if the direction of current are opposite, the magnitude will be same, only the directions will be different. Repulsive forces will be acting, magnitude wise it will be same, no problem for magnitude wise. If the directions will be same, then it will be attractive force. If directions are same for the current, it will be attractive force. Magnitude will be still same. There is no problem in the magnitude. Now let's come to a device that is moving coil galvanometer. Galvanometer, where we have studied, correct, exactly in the last chapter I have told you that I will discuss more about galvanometer, what is happening inside the galvanometer. I think that there is some lag, or is it fine? Is my voice is clear to everyone? Okay, I hope that it is clear. There is no problem. Fine. So let's start. Moving coil galvanometer. What is moving coil galvanometer? What is galvanometer, students? Tell me. Galvanometer is a device which is used to measure very small current. It is used to detect very small magnitude of current. What is a complete phenomena? Actually, two strong magnets are fixed inside a galvanometer, and there is a. If I will tell you about the what is the inside portion, there is a moving coil. Okay, there is a moving coil winded by a lot of, and the core is made up of iron, and this coil is moving. And this is representing you a lot of windings. That means what we call winding, number of turns. This is reflecting you what number of turns it is winded by wires. And then there is a strong magnet, north pole and south pole, and what I will be telling that the direction of magnetic will be from north pole to south pole, moving like this. This is the direction for magnetic field. Due to that, what will be happening? Now understand. There will be some torque will be applied. See here the current, it is now connected by, this is the galvanometer. Now it is connected by terminal 1 here and terminal 2 here. It is reflecting terminal 1 written as and terminal 2. Now what will be happening when the current will be coming? There will be some torque that will be acting, correct? If there will be some torque, it will start rotating. It will the core, iron core is there, the moving coil that is there, it will start rotating. And how you will be writing how much torque will be acting? Torque you will be writing. And now understand that also, that what is the direction between the torque is written as m cross b, correct? M cross b. So what is the direction with angle between the magnetic field vector and the magnetic moment? How you calculate magnetic moment? How you calculate? This is the direction for magnetic moment that is coming outside the plane, and what is the direction for magnetic field, that is b. That means can I say theta is equals to 90 degree? Simply I can say torque is applied equals to m into b. And what I can write for m? M is nothing but I current into number of turns into area. Area, whatever the area of this coil is will be there, it will be area, and into b. This is what I can say torque due to the current that we have studied. Due to the flow of current, this will be the torque that will be coming, correct? Now if this is rotating, in SHM you have remembered a term. What I am asking you, in SHM we have studied about a term torsional pendulum. Torsional pendulum. This is a very simple thing. Let's suppose you have hinged something here, and you are rotating it continuously. There is a string attached and you are rotating something, and when you will leave, what will be happening? What will be happening? Now it will be coming back again to its normal position. So what is that? This kind of rotation is called as torsional pendulum. Okay. So what will be happening due to that? Due to this rotation, see, I can say it depends on the angle by what you have rotated. So torque due to this rotation, it will be coming equals to c theta. Let's write it c into theta. So I can say both the torque will be equal. Torque due to current is equals to torque due to restoring force, and how much torque due to current I have written b into n into a bina is equals to c into theta. That means what I can say about the current can be written as c theta divided by b into n into a. C theta divided by b into n into a. This will be the current. Now there are two very specific terms here. One is called as current sensitivity. Second one is called as voltage sensitivity. The both are derived from here only. I will tell you the formulas for them also. Current sensitivity, from here only it is defined as theta by I. Theta by I can be written as b n a divided by c. B and a divided by c. This is called as b and a. This is defined as current sensitivity. This is called as phi by or theta by I. It is called as, the term is current sensitivity. Current sensitivity. I will tell you. It is also defined separately here. Current sensitivity is a term B and A divided by C. This is current sensitivity defined as deflection per unit current. Deflection, how much deflection is coming, that is how much angle by which it is showing deflection. Current divided by area. Angle divided by current is defined as current sensitivity. It will tell you how sensitive your device is. Okay, and you know that galvanometer is very high sensitive device. Okay, from even in the very small currents also it shows a very deep deflection. Okay. If I'll ask you similarly for voltage sensitivity, how you will define? That is defined as angle theta divided by current. Current can be written as what? V divided by R. V divided by R is equals to whatever it is written. So this R will be going here. It is defined as, take it here, N A B divided by C into R. This will be defined as voltage sensitivity. Voltage sensitivity. Just remember the definitions of these things. That will be sufficient for you. Voltage sensitivity. If it is coming here, you can see angle. It is defined as deflection per unit voltage. It is defined as voltage sensitivity. This is the deflection. This is the voltage. Deflection per unit voltage is voltage sensitivity. So this was all about this chapter. I hope that you got to learn a lot of new things about magnets. Okay, the next chapter is also about magnets. Now we will be seeing the further effects, how that current is, if current is induced, there will be some potential also, correct? There will be some flux also we will be discussing. All these things we are going to discuss in the next chapter, that is electromagnetic induction. Faraday's laws, Lenz's law, all these things are very interesting. I will tell you, we are going to deep dive into the complete depth of magnetism. So until next time, keep learning, keep growing with Tapasya and Digu, and then Digu Nama Tapasya.